Now we move from rollup architecture to the user journey. Rollups start to feel real through wallets, bridges, dApps, explorers, and network switching. As we go, watch for where friction appears, because UX directly shapes trust, liquidity, and adoption. So far, we've covered why Ethereum gets congested, how it anchors trust as a settlement layer, and how Layer 2s help. This section shifts from architecture to practical rollup use: wallets, bridges, apps, transfers, and explorers. Most users never interact directly with a sequencer, settlement contract, or proof system. They experience a rollup through familiar interfaces. The wallet manages network choice, balances, signing, and gas. A bridge guides movement between Ethereum and Layer 2. dApps provide the activity itself, such as swaps or lending. Explorers make the invisible visible by confirming transactions, contracts, and asset movement across the system. A typical rollup journey starts in the wallet with the right network selected and gas available. From there, assets are bridged into the ecosystem, which may introduce delays or liquidity surprises. Once funds arrive, the dApp still needs to support that rollup. Then comes signing, confirmation, and status tracking through wallet alerts or an explorer. Frustration usually appears at the handoffs: wrong networks, missing gas, slow bridges, or unclear status. For most users, the wallet is the front door to rollups. It stores or connects to keys, signs transactions, shows balances and NFTs, and estimates fees before anything is submitted. Because many rollups are EVM compatible, the same address can often work across Ethereum and Layer 2 networks. That convenience depends on clear network switching and approval flows. When the wallet experience is confusing, rollups feel fragmented and risky, even if the underlying technology works well. Before a wallet can use a rollup, it needs that rollup's network details. Switching networks tells the wallet where to read balances, estimate fees, and send transactions. The chain ID identifies the destination chain and helps prevent replay mistakes. The RPC endpoint connects the wallet to live network data, while the explorer, currency symbol, and network name make activity understandable. If any detail is wrong, transactions may fail, or balances may appear to be missing. Wallet prompts are where intent becomes authorization. A transaction approval usually costs gas and changes on-chain state, so users should verify the action and destination. A signature may feel safer because it often uses no gas, but it can still prove identity or grant permissions. Token approvals deserve extra attention, since they can let a contract spend tokens later. Clear prompts help users spot risk, avoid phishing, and approve with confidence. Rollups reduce fees, but every transaction still needs gas to pay for computation and network resources. The important question is, which token pays that gas? Many Ethereum-aligned rollups use ETH, so users can bridge ETH and keep a familiar fee experience. Other networks require their own native token, which can surprise users who have bridged assets but still cannot transact. Some apps hide or sponsor gas, improving UX while also making fee rules less obvious. When using a dApp on a rollup, the interface may feel familiar, but the backend is network-specific. The wallet determines which environment you are interacting with, and the dApp routes you to contracts deployed there. Ethereum, Optimism, Arbitrum, or another rollup can each have different contract addresses, token support, liquidity depth, exchange rates, and fees. Before approving, always confirm the active network. Explorers turn a wallet message into verifiable facts. Start with the transaction hash, then check status confirmations from and to addresses, value, and gas fee. With rollups, network context is especially important. A swap or transfer may be recorded on Layer 2, while a bridge can also create related Layer 1 activity. If something looks missing, first confirm that you are using the correct explorer before assuming the transaction failed. A bridge is the coordination layer that lets value move between Ethereum and rollups. Assets usually do not teleport. Instead, the bridge locks funds in one environment and credits a representation in another. Depositing moves value into a rollup. Withdrawing reverses the process, often with a waiting period. Canonical bridges come from the rollup ecosystem. Third-party bridges can feel faster, but they add extra trust and operational risk. With a canonical bridge, users follow the Rollup's official path. They connect a wallet, choose the asset and amount, then submit a deposit from Ethereum mainnet. That first transaction can be expensive because it pays Layer 1 gas. After Ethereum confirms it, the bridge verifies the deposit and credits the user on the Rollup. The trade-off is clear: less added third-party trust, but often slower settlement and a less flexible experience. Withdrawals are not always just deposits in reverse. To move funds back to Layer 1, the system may need to prove what happened on the Rollup, then wait for the security window to close. In some designs, that can take days. Faster bridges or exchanges can reduce the wait, but they introduce different trust, liquidity, or cost assumptions. The UX lesson is simple: show status, timing, and the next action clearly. Rollups can be technically fast and cheap, yet still feel difficult to use. The main friction points are scattered liquidity, slow or confusing bridges, missing gas tokens, and onboarding steps that overwhelm new users. The big takeaway is that Rollup UX turns scaling infrastructure into something people can actually use. Wallets shape access, bridges move assets with trade-offs, and dApps and explorers build trust. The main frictions are liquidity, delays, gas confusion, and onboarding. Next, we'll unpack ZK Rollups, starting with zero-knowledge proofs.